Welcome to our little curious podcast, Hidden Synapses. For decades, physicists believed nature treated left and right the same, until one woman shattered that belief. Chien-Shiung Wu's legendary experiment on beta decay changed the laws of physics forever. But when the Nobel Prize was awarded for the discovery, she was left out. Why do some scientists get erased from history? Let's dive into the story of the woman who rewrote the rules of physics. Chien-Shiung Wu's journey from a small town in China to becoming one of the most influential physicists of the 20th century is a testament to both scientific brilliance and perseverance against discrimination. Born in 1912, when female education was rare in China, Wu benefited from her father's progressive views on gender equality. This early support proved crucial in launching her remarkable scientific career, as she excelled in mathematics and physics from an early age, demonstrating the exceptional abilities that would later revolutionize our understanding of the physical world. After distinguishing herself at Nanjing University, Wu made the bold decision to pursue advanced studies in the United States. In 1936, she enrolled at UC Berkeley, studying under Ernest Lawrence, whose cyclotron would revolutionize particle physics. This period laid the groundwork for her future experimental expertise, though few could have predicted the seismic impact she would have on modern physics. Her specialization in beta decay and nuclear physics would prove instrumental in her most significant contributions to the field. The pivotal moment in WU's career came with what's now known as the Wu experiment. In the 1950s, physicists universally accepted the principle of parity conservation, the idea that nature treats left and right symmetrically at the subatomic level. When theorists Sung Dao Lee and Chen-Ning Yang suggested this might not always hold true, Wu designed an ingenious experiment using cobalt-60 to test their hypothesis. Her meticulous work proved that parity conservation is indeed violated in weak nuclear interactions, fundamentally changing our understanding of the universe and the forces that govern it. Despite the groundbreaking nature of her work, Wu was notably excluded from the 1957 Nobel Prize, which went solely to Li and Yang. This oversight exemplified the broader discrimination women faced in science, where experimental work, often conducted by women, was frequently undervalued compared to theoretical contributions, typically dominated by men. As Wu herself noted, it is shameful that there are so few women in science. The prevailing attitude of male physicists at the time, who dismissed experimental work as secondary to theory, contributed to this systematic undervaluation of her contributions. WU's scientific impact extended far beyond the parity violation discovery. During World War II, she contributed to the Manhattan Project, where her expertise helped improve uranium enrichment processes. Her book Beta Decay became a cornerstone text in nuclear physics, demonstrating her mastery of both theoretical understanding and experimental technique. In 1975, she broke another barrier by becoming the first woman president of the American Physical Society, paving the way for future generations of female scientists in leadership positions. Throughout her career, Wu accumulated numerous prestigious awards, including the Wolf Prize in Physics and the National Medal of Science. These recognitions, while significant, perhaps still fell short of acknowledging the full scope of her contributions to modern physics. Her experimental techniques and insights into beta decay and weak interactions helped establish the foundation for today's standard model of particle physics, influencing countless subsequent discoveries and theoretical developments. Wu became an outspoken advocate for women in science, regularly challenging the systemic barriers that prevented women from receiving appropriate recognition for their work. Her advocacy, combined with her scientific achievements, made her a role model for aspiring female scientists worldwide. She demonstrated that experimental physics was just as crucial as theoretical work, and that women could excel in fields traditionally dominated by men. In 2021, the U.S. Postal Service honored Wu with a commemorative stamp, a recognition that underscores her lasting influence on American science. Often called the First Lady of Physics, WU's legacy extends beyond her scientific achievements. Her career serves as both an inspiration and a cautionary tale about recognition in science. While her work fundamentally altered our understanding of the universe, the Nobel Prize oversight highlights how institutional barriers and gender bias have historically undermined women's contributions to science. When Wu passed away in 1997 at age 84, she left behind a transformed scientific landscape. Her story continues to remind us that scientific progress depends on both theoretical insight and experimental brilliance, regardless of who provides them. The comparison often drawn between Wu and Marie Curie reflects not only their scientific achievements, but also their role in breaking down barriers for women in physics, making WU's story as relevant today as it was during her groundbreaking career. Today, every physics textbook acknowledges that the universe isn't symmetrical, thanks to Chien-Shiung Wu. But what if her contributions had been recognized in her lifetime? Science moves forward, but justice often lags behind. Wu may not have won the Nobel Prize, but her legacy in physics is undeniable. The universe may be unbalanced, but her impact is not. Thank you for joining me on this journey through the life of Chien-Shiung Wu. If you enjoyed this episode of our podcast, Hidden Synapses, don't forget to subscribe and share. And if there's another underrated scientist whose story you think should be told, let us know. We'd love to explore it in a future episode.